No, no, it's all like, it shows up in math and just how actually like mechanically advanced they were.
So today I have a sort of odd collection of things to tell you guys about, and I'll try to be somewhat explicit because the first thing I'll try to be somewhat explicit about for sure, because I think there's like a homework problem like it, and but anyway, let me just get into it. Today I want to talk to you about encryption. So do you guys know what encryption is?
Yeah.
With computers? Yeah. So, I mean, it's an ancient story, right? Like, you have information, you're trying to pass it between people, and how do you maintain secrecy, right? And so, the first sort of elementary technique is what you'd call the Caesar, I can't spell it, Caesar shift or something like that. So the idea there is pretty simple, right? You come up with a code. Well, I mean, usually, for the sake of our English discussion, we usually have in mind something like A equals 0, 1, B equals 0, 2, C is 0, 3, etc. You get down to J is 10, so forth. Z is 26, right? So you can use these numbers to represent, letters. And of course, the Caesar shift would be something like, I mean, it's very, very silly, really. You could take something like cat, right? And cat would be what? It would be something like, it's a triple, right? C is what? 03, 01, T. Why did I do myself T? 20. All right, there we go. 20. I might be wrong. Well, 20 feels right. It feels right. So the Caesar shift is very, very rudimentary. It basically just says shift, just like add, basically. Pick whatever shift you want. We could say, add 3, for example. So cat would get encrypted to 0, 6, 0, 4, and 23, right? And of course, you could think, well, like, what is that actually in terms of letters? That's what? F, D, 23 is what? U, fadoo. So cat becomes fadoo, right? And then you can say, kill the fadoo, and then no one will know what you're talking about, right? Except for those who are in the club that realize you're using a Caesar shift of 3. Now, this is not a very reliable encryption technique, obviously, because it doesn't really take much data at all to undo it. One of your homework problems is like this. I've instructed you. It's not the method your homework problem. It's not like this. It's a little bit more complicated. In the homework problem, I've advocated this kind of shift, something like the message. Excuse me. Let me call it X. So you've got take your letter X, and you're doing it something like MX plus B. And I tell you what one 3-letter string maps to another 3-letter string, right? And that's enough information to fix the values for M and B, and thus to tell you how the
it's like point slope.
Yeah, it's like point slope. Essentially, I'm giving you enough data to fix that. That's a little bit more complicated than a simple shift, right? Yeah. And then to undo this, okay, so all of this is done mod 26, all right? Because if you get to 27, you go back, all right? If you get to 28, you go back to 2. It's a B again. So it's all done. All of this is done with like respect to that idea. And so to undo this, mod 26, what you'd have to do is find what's the inverse function to that mod 26. Well, you have to find the multiplicative inverse of m mod 26, whatever that is in your homework problem. Here, for example, if we had, it was a 13?
It depends on what letter, actually.
Well, m should be the same. Like this is the encryption formula for that homework problem. All right.
Yeah, well, m.
So let's just for the sake of discussion, suppose it's 13x plus 2. I'm not saying it's that. Suppose it is. Right? How do you find the inverse function for that mod 26?
Well, you need to find the identity. Right?
Yeah. I mean, basically, we solve this. We set this equal to y, solve for x, right? So we've got 13x equals to y minus 2. And then the question is, what's the inverse? Oh, no. What have you done to me? 13 has no inverse mod 26. Right?
Can't multiply 13. Oh, yeah, because it's
The greatest common divisor of 13 and 26 is 13, I believe.
Oh, yeah.
See, so they're not relatively prime. 13 is not a unit, mod 26. So that better not be what I did to you. Yeah. Instead of 13, let's say, 11 here. Okay, 11 is relatively prime to 26. So you could find what's the inverse of 11 mod 26.
Multiply 11 by 22. Oh, man, that'd be a lot.
How would we figure out the inverse of 11 mod 26? Let's go through it.
How I've done it is how many times you multiply 11 to get your 1 back.
How many times you multiply 11 to get your 1 back?
Yeah, because, if you do 11 times 11, or 11 times 2, that's 22. So
That's not a bad idea. That's not a bad way. You just keep multiplying 11 until you get to 1.
you're going to see it in that homework.
Well, let me show you another way. What we can do is this. 2611 is a comma v, all right? So we'll use the Euclidean algorithm, vector Euclidean algorithm right here. 2611. Our goal is to find 11 inverse in Z26. Okay, that's what I'm doing. And, all right, so what we got? So the rule is we bring the 11 down. 26 divided by 11 has a remainder of 4, because 26 is 22 plus 4. So I got B, I got A, and I have to, so I'm taking 26 and I'm subtracting 2 copies of 11, so I do A minus 2B. All right, great. Now I bring the 4 down. 11 divided by 4 has a remainder of 3, right? So I do A minus 2B. And how do I get that 3? That 3 is coming from 11 minus 2 times 4. So that's B minus 2 times A minus 2B here. That's how we do that. Let me clean it up just a bit. So we've got A minus 2B and minus 2A. That's 4 plus 5B, I believe. All right. So then we bring the 3 down, and our 4 divided by 3, remainder 1. Good, we're done. So that's minus 2A plus 5B. And how did I get the 1? I got the 1 from 4 minus 3, right? I got the 4 from 1 minus 3, which means I get that 1 from A minus 2B minus parentheses minus 2A plus 5B. See, that's how I got that 1. And so I look at that, I clean it up. What do I got? I've got how many A's?
Should have 1. No, I mean 3 A's.
3. Okay, 3A. How many B's do I got? Minus 7B. All right, so that is equal to 1. But remember what A and B are? 26 and 11. Yeah. So what that tells me is that 1 is is equal to 3 times 26 minus 7 times 11. Right. So what that tells me, though, I look at that equation and I must interpret it modulo 26. Modulo 26, that reveals that the inverse of 11 is minus 7. So this tells me that 1 is equal to minus 7 times 11 mod 26. In short, goodness, I'll just put it here. 11 inverse is equal to minus 7. Now mod 26, add 26 if you don't like a negative number. What's 26 minus 7? It's 19, right? So there you go. The inverse of 11 is 19. So if I wanted to undo this affine shift cipher here, this affine shift cipher, I could solve for x equals to, I multiply this equation both sides by 19. 19 times 11x is equal to 19 times y minus 2, right? Therefore, x is equal to 19 times y minus 2. Just to complete the thought here, f inverse of y is 19 times y minus 2. And so that formula right there, I could use that to undo a shift. So this is more complicated than just when you multiply by a number mod 26. That's a more complicated operation than just shifting the Caesar shift, right? But even after all this, and so like, I'm very proud of the homework problem I gave you. Did you finish it, Audric? Or?
Mission 3?
No, where was the one I had for the encryption problem?
Encryption?
Was that in mission 2 or was it mission 3?
It wasn't in mission 2. I would have noticed it.
Oh, maybe it's in mission. Maybe it's in mission 3, but I'm very. You'll appreciate the message that I've encrypted. All right, so it's something rather silly. The larger point here in all this is just that this is not a very good way to do things because it takes very little. Like once somebody else figures out this is what you're doing, it's really not very secure because all you got to do is calculate this one inverse and like solve the formula. You can undo these formulas pretty simply with like a little bit of suspicion on how the encryption is being made, right? This, of course, is not how encryption works on the computer nowadays, right? So the encryption that we use, to guard bank transactions and email and everything else is something much more sneaky, all right? So let me try to, I just wanted to start with this little discussion of naive encryption just to kind of wet our whistle, all right? And also because I think it's good to see this calculation, right? Okay, so let me describe to you what's called RSA encryption. Now RSA encryption, it's those are names of people. Let's see here, Rivest, Shamir, and Edelman. They found this in 1978. That's when I was born. It's kind of an old idea. And apparently it's not just them. This was kind of in the water. There's also a British intelligence officer by the name of Clifford Cox who invented the same trick in the early 70s, apparently. And I'm, of course, describing to you a naive version of this, all right? With any kind of encryption scheme, there's always like more nuanced things, and there's probably like error checking schemes and things like that. I'm not really getting into any of that. But let me just get to it. This is the RSA encryption idea. So let me just write it out here. Number 1, you choose large prime numbers, P1 and P2, all right, in form n equal to P1, P2. And when I say large prime numbers, I'm talking about prime numbers that are hundreds of digits. Hundreds of digits. All right, so if I tell you I have the number 1,700,050,362, and then I say, is that prime? You don't know. Well, I said 2. That makes it easier. Make it an odd number, right? I mean, if it's even, it's not prime.
Yeah.
But replace that last 2 with a 1. Is it prime?
No idea.
No idea, right? It's actually a very computationally intense problem to figure out whether or not a number has is prime or not.
Is that why like the infinite prime theorem was like a big deal for a while?
That there are infinitely many primes? I mean, I think that's, I don't know, I mean, why is that a big deal to ancient Greek people? I don't know.
Oh, okay, they solved it back then.
Yeah, I mean, this is a theorem of Euclid, right?
Yeah. Oh, yeah.
I mean, we've known about the infinitude of primes for a long time. But it is just a computational fact that it is very, very difficult to decipher prime factorizations of large numbers. It is a computationally just insurmountable problem. I mean, short of what's called a quantum computer. There's hope for better factorization schemes using what are called quantum computers. When this book was written, there weren't any quantum computers. Since the book has been written, there have been quantum computers made with several bits, but they're really not, I'm not sure like how far we've gotten with that, but in a few years ago, I forget who made it, but there have been a few.
And that's like just based on because we do on and off, like they can be put in a state of both on and off or something like that.
Yeah, the way quantum computers work is different. It involves this, I think essentially, I mean, just, I'm probably butchering it, but it allows some kind of like massively parallel processing kind of thing, but it has to do with the details. It'll allow you to do things in polynomial time that wouldn't be possible with a traditional computer, but I'm not an expert on all that. Like that's still very much where the cutting edge of theoretical computer science / physics people are like trying to do quantum computing. Partly because it would break encryption. It would ruin this. Is the fear. Now, okay, so you choose a pair of large prime numbers and you multiply them. We know how to multiply large numbers. It's tedious but straightforward school arithmetic. So the product of two large, and n is huge. Now, keep in mind, you're not telling everyone what P1 and P2 are. But you tell everyone what n is. So you share.
Oh, that's a kind of prime factor. Oh, man.
You share n, P1, P2, but others don't know P1 and P2. All they know is the product. All right? Then step number 2, you calculate I'm sorry, I can't follow my own stupid stupid algorithm. Anyway, so you've calculated. I'll put a D on there. Calculated n equal to P1, P2, right? Okay, great. And you choose what's called an encryption exponent. All right, encryption exponent. We'll call that E, where the GCD of E and phi of n is equal to 1. Now notice phi of n, what is phi of n here? That's the Euler phi function of n. All right? Now, again, number 2, you share E publicly, all right? But the mechanics of how you chose that, only you really understand. All right, and we can say more about that because what is phi of n? Phi of n is phi of P1, P2, right? But remember, the Euler phi function is multiplicative. And in P1, we're saying P1 and P2 are distinct primes. So this is phi of P1 times phi of P2. But these are primes. So that's straight up P1 minus 1, P2 minus 1. So like since you know the primes, you're able to calculate phi of n explicitly. It's not a big deal. And then you choose an encryption exponent E. All right? Step number 3. You publish, I can't spell publish today. Publish E and N for anyone who wants to send you a message. And the message we're going to use, we're going to call that message M. Now, keep in mind, we're going to talk about a message as if it's just one letter, but of course you could repeat this. You could do it like letter by letter. So I'm just focusing on just how to encrypt just one single letter. All right, one single letter. All right, so step 4, your friend uses the alphabet code for the sake of discussion, all right, like we talked about, to convert a message, a letter, to a number, right? For example, the message we'll look at when I actually put numbers into this, I'm going to actually work through this with numbers. When we do that, we'll look at the message being J. So M will be equal to 10. All right. That's part number 4. 5. All right. Your friend takes the N and the E which you published, and they run their message through the encryption map. Your friend, let's say, encodes message M to f of M, which is simply equal to M to the encryption exponent. All right? Mod n, by the way. Mod n. Modulo that huge N. All right? So, and then he just shares it. He just tells the world. I mean, it doesn't matter if it gets intercepted. Whatever it is, it is. All right? So they communicate f of m, which is m to the power e, to you. And then here's where the cool part happens. 6. All right? You know P1 and P2. You know phi of n. So let's suppose you have E times D equals to 1. E times D equals to 1 mod phi of n. Suppose you can find an inverse of the encryption exponent modulo phi of n. All right? Now, let me do a little calculation over here. Let's work it out. M, oh no, M to the E to the D is equal to M to the 1 plus K times phi of n. How do I know that? Oh, right. So since this is equal to, since ED is equal to 1 mod phi of n, that means that E times D is 1 plus some multiple of phi of n, right? Yeah. But then what? That's a K. Here K is some, integer. All right, but what is that? This is equal to m to the 1 times m to the phi of n to the k by laws of exponents, right? But what is Euler's theorem? What does Euler's theorem say about m to the phi of n mod n? Euler's theorem, remember, Euler's theorem says that x to the phi of n is equal to 1, if I remember right. It's equal to 1 mod n. Is that right? I believe that was Euler's theorem. Audrey's like, I wrote everything down. It's the very end, the bitter end of my group theory, jibber jabber.
Euler's theorem is if x is in UK, then x to the phi of k is 1 on k.
Right, so take that k and make it an n, we're in business.
Oh, I wrote this for
Cool. So that's Euler's theorem. What does that mean? Well, that means that this piece is 1. So you got m to the 1 times 1 to the k. In other words, you got m. So for this reason, we call D the decryption exponent. See, because it's so much easier, actually. It's so much easier than like the affine shift thing I was just talking to you guys about. It's literally, you just power it up with the encryption exponent, send it to your friend, and then your friend, since he knows how he made his encryption key, all he has to do is take your message and power it by the decryption exponent, and he's uncovered the message.
Oh, so only the host, like if your friend's the person and you're the host, only the host has the decryption.
Only the host has the decryption, right?
Yeah.
Exactly.
So it wouldn't matter how much your friend knew or didn't know because you never had the decryption.
Right, right. I mean, unless you're so foolish as to say, oh, here's the decryption exponent, but
Yeah,
that would
no,
just,
yeah.
I mean, you'd have to work for the government to do something like that. Right? Sorry. I guess I work for the government. What am I talking about? I mean, technically. Okay, so let's look at a specific numerical example of how this goes. All right? So I'll work it over here, actually. Example. All right, so here it goes. 1. We'll let P1, I mean, this is going to be kind of a toy example, obviously. P1 equals 13, P2 equals 17. All right, so with those being our, primes, that makes n, P1, P2 would be 221. All right, step number 1. Step number 2, we can calculate phi of 221. That's phi of, 13 times 17, which is phi of 13 times phi of 17, which is 12 times 16, which is 192. So I'm going to choose the encryption exponent E equal to 37, since, the GCD of 37 and 192, I think it's pretty clearly equal to 1, right?
And 12 and 16, those are what it takes to get inverse.
12 and 16. Well, since 13 and 17 are prime, the group of units is just one less. So like anytime we have Euler phi of a prime, it's just the prime minus 1. And of course, it's multiplicative, so if they're relatively prime, we multiply. All right, so just to emphasize here, 3, my n is 221, and my encryption is 37. All right, that's what I share that publicly. All right. Again, as I was saying, my friend decides to send me the message J, m equals 10, message J, all right? That's my, and so then my friend is going to encrypt that message, all right? Now here's where the calculation gets a little messy, because this is where the, I guess rubber hits the road, whatever you want to say. But so 5, my friend to actually do the encryption, we got to calculate 10 to the 37 mod 221, right? So how do we do that? Well, let me recommend the following scheme. 37 is 32 plus 4 plus 1. So if I can calculate, the 4th power and the 32nd power of 37 mod 221, then I just multiply them. And let me just kind of throw some things up here. So first of all, m squared is 100. M to the 4th is 100 squared, right? Which is, by the way, equal to 55, all right, mod 221. This is all mod 221, all right? So how did I get that 55? Do you guys want me to tell you? What's my technique? So here's what I do in terms of calculator work. All right, so what you do is this. So I'm trying to figure out what is the residue of 100 squared mod 55. So what I do is I take 100, I square it. That gives me 10,000.
Oh, I see. Oh, yeah.
Gives me 10,000. Then what I do is I divide by 221. All right, so I'll just over here, okay? 10,000 divided by 221, and then I hit the handy-dandy decimal number, and I get 45.24, blah, 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 whatever. The point to that is that there's 45 copies of 221 in 10,000. So my next move is to subtract 45. I subtract 45. So I do 10, this number, minus 45, and that gives me 0.24, blah, 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 blah. All right? 0.24, blah, blah, blah does not delight me. I take that, I multiply by 221. I get 55. So and that is how I learn that 100 squared is congruent to 55 mod 221. What I do is I divide by 221. That shows me the integer piece. I subtract off the integer piece, and then I simply multiply by the moduli to figure out the remainder. This is a fast way to find remainders. Now, continuing here, m to the 8th. Let me just kind of like, m to the 8th works out to 152, m to the 16th works out to 120. M to the 32nd is, I'll work this one out. I'll work this one out. This is 120 squared. 120 squared, right? So I take 120 squared. That gives me 14,400. I divide by 221. It has 65 point something. So I subtract 65. It leaves me 0.158, blah, 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 blah. I multiply by 221. I get 35. So this is congruent to 35. All right. Okay, now I have everything I need. I have everything I need to calculate this because 10 to the 37 is equal to 10 to the 32 times 10 to the 4 times 10 to the 1. All right, I'm calculating mod 221. Calculating mod 221, so I know that that's actually 35 times 55 times 10. And you can multiply those. They're not big. 35 times 55 times 10. Now, the way I'm doing this, it's not written in stone. There's other ways to do it. You know, this is just a way. I get 19,250. I divide by 221. That gives me 87.1, blah, 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 blah. Subtract 87. All right, multiply by 221. I get 23. So 23 is f of m. This is the encrypted message that your friend sends to you.
All we have to do is raise it to the D.
Right. Now, keep in mind that we have to kind of, in this story, you have to imagine that you didn't know that it was 10, right? We didn't, I mean, your friend just shared this. Now you figure out the secret message, you raise that to the decryption exponent, D. Oh, we don't know the decryption exponent yet, do we? We still have to calculate that, don't we? So how do we figure out D? Whew. Starting to feel a little lightheaded. I think I'll be okay though. All right, make sure I can see everything here. Let me give you yet another example of the vector Euclidean algorithm calculation, because that's really, I've done a lot of these things now, and I'm more and more of the opinion that like that's the way to do it. So we need to calculate, we're trying to calculate E inverse, which we're calling D, mod what? Phi of n, right? Remember, it's mod phi of n that we calculate. That's the kind of quirky thing here, right? A lot of the calculations are done mod n, but in the middle of this, you figure out the decryption exponent using a phi n calculation, right? And that's part of the magic, because figuring out what phi n is something we can easily do because we know the primes that are forming the key, whereas somebody else wouldn't. But anyway, so we're trying to figure out 192, and our decryption is 37. We're going to call that AB. So we're going to go through that same song and dance here, right? So that's bring the 37 down, and that gives you actually a remainder of 7. And so that was A minus 5 times 5 copies of 37 in 192, actually. All right, so like that. We bring down to 7. Remainder 2, right? We subtract off 5 copies, so we got to do B minus 5 times A minus 5B. And then what do you got here? Well, 2 and the remainder, 7 divided by 2, remainder 1. Wonderful. That means we're pretty much done. Now this is minus 5A plus 26B. Now to get the 1, we needed 7 minus 3 times 2. So that becomes A minus 5B minus 3 times minus 5a plus 26b. I'm just using,
Yeah.
I cleaned it up, this is that, right? And lo and behold, we're at the end of the line here, so to speak. What's this work out to? Well, this works out to 1 is equal to how many a's do I have? 15 plus 1, 16a. And how many b's do I got? 81.
26 times 3, 78 plus 5, so 83.
83, okay, so yeah, minus 83b, right? All right, let's demystify it. Remember, a is 192, and b is 37. So this shows me that my decryption exponent is minus 83. So, and we're working mod phi of n, right? Which is mod 192. So you want to add 192 because nobody wants to take the minus 83 power, So 192 minus 83, 109 is our decryption. So 109 is our decryption exponent. All right? So let's do it. Let's decrypt. So 7. We're going to take our message, which was 23, and we want to raise it to the 109 power. 109 power mod 221. Right? So how does that actually go? Well, let me talk about it. So here's some of the sub-calculations. I do 23 squared. That's 529, but that's congruent to 87 mod 221. I do 23 to the 4th. That's 87 squared, which is 7,569, which, by the way, is congruent to 55 mod 221. 23 to the 8th is 152. 23 to the 16th is 120. 23 to the 32nd is 35. 23 to the 64 is 120. So all of these are done with the same bag of tricks I just showed you guys, the previous exponentiation song and dance. And notice that 109 is what? It is 64 plus 32 plus 8 plus 4 plus 1. So that's the strategy here.
So you use factors of 2, like additive factors of 2?
Yeah, additive factors of 2 is, this is binary, this is the binary exponentiation trick. It's part of what makes encryption computationally feasible as well, because this is a fast algorithm. Not only are you not only are you just doubling, you're able to simplify mod n as you go, and so like that's part of what makes encryption a feasible calculation to actually put into practice. So 23 to the 109 is going to be 23 to the 64 times 23 to the 32 times 23 to the 8th times 23 to the 4th times 23 by laws of exponents. But the thing is, you've already calculated those mod 221, so you just put them into practice, You use, okay, so that's like 120 times 35 times 152 times 55 times 23. And 120 times 35 is 4,200. Resist the temptation to multiply these all out. Treat them a little bit at a time, all right? Bite-sized pieces. The other one is 192,280. Now for me, these I can handle with my calculator. The first one is congruent to 1. The second one is congruent to 10. We get 10. We have discovered the message is 10. So they sent us the hidden message 23. We ran the decryption. We got back to 10. This is RSA encryption. The security of the method rests on the impossibility of taking that public key encryption N and cracking it and learning what those 100-digit primes that are multiplied to form the N are. This is how encryption works. It seems magical that it's possible to share publicly the N and the E like that and yet have security, and yet we can.
No, but it makes sense. I mean, the factorization of that at whatever large.
Yeah. But that's it, guys. I mean, that's RSA encryption in a nutshell. And it's all, and so the hilarious thing about this whole thing, right? The absolutely hilarious thing about what we're doing right now is this is all born of number theory, right? I mean, it's very much, you know, Euler's theorem and modular arithmetic, all these things. This is, you know, part of the queen of mathematics, if you will. And, you know, there were mathematicians in the early 20th century who were so proud of the fact that their number theory, their precious number theory, could never be applied to the real world. There is no more applied math than this. Every email you send, every bank transaction, it's all roughly based on this, the security that we have. All right. So, next topic. I just want to say a word about quadratic Diophantine equations. I'll try not to talk too long about these. So Diophantine, remember that's that Diophantus, the ancient Greek, remember? And so this is part of a sort of a larger story in number theory. I think it's best for me just to give you an example. All right. X squared plus y squared equals to p has no solution for p an element of 4z plus 3. This is the claim. So it's a you see why it's called quadratic, right? I mean, that's not particularly surprising. Tell you what, let's before I show you the proof of this, let's just try to take stock in what this theorem is saying. The question is, what kind of numbers can you get from x squared plus y squared? Squared numbers? I mean, let's try it out. Like,
X and Y is
let's just
right?
let's put in some numbers, right? Like, how about 1 squared plus 2 squared? What do you got?
5.
You got 5.
This is X, Y, and Z, right?
There's no z. I mean, we have looked at x squared plus y squared equal to z squared before. That would be the discussion of Pythagorean triples.
Yeah. No, I'm talking about like this question of we're not using X and Y on real, like they can't be real numbers.
No, x and y have to be integers here.
Yeah, that's what I meant.
Oh, yes. Here, it's assumed x and y are in the integers. Yeah, that is presupposed here. Yes, thank you. But we'd try something else. Like, how about 3 squared plus 10 squared? What do you get?
900. But
9 plus 1, yeah, 109, right?
yeah, did that backwards.
How is, I mean, is 5, so in terms of what's in 4z plus 3?
0, 1, 2,
4z plus 3 is things like what? 3, right? 3 plus 4,
Oh,
7, 11,
I was thinking mod 4.
15, right?
Mm-hmm.
What 109, is that one of these? I mean,
Well, we could subtract 3, divide 4.
you subtract 3. Okay, so 109.
So yeah, 106 divided by not divisible by 4, so no.
No, it's not one. It misses that, right?
Yeah.
You could figure out which one of those guys is close to it, but it's not there. And the thing is, you can keep plugging numbers in all day long, and you're never going to find a p which is of the form 4z plus 3. That's the claim here. I mean, you could discover this claim numerically, right? I mean, you just plug numbers in and kind of look at patterns and go, oh, it's never that form, huh?
No, but there's something to it.
So how do we prove this claim? Well, check it out. Check it out. So, no, goodness gracious. Here's the proof. Oh, you have an idea, Roderick?
I do, but no, I'd rather be told.
You do, but you'd rather just be told. It's
If you gave me this for like a day, I'd try to figure it out.
fair enough. It suffices to show that x squared plus y squared is not congruent to 3 mod what? Mod 4. See, that's what it would mean for there to be a p there. It would mean that that kind of p was 3 plus a multiple of 4. So to say otherwise is to say it's not equal to that. Right? So how do you determine x squared plus y squared is not congruent to 3 mod 4? Well, you check cases. There's only a few cases to check. So you just need to check, right, x comma y congruent to basically 0, 1, 2, or you could use minus 1 rather than 3, you know. Minus 1 is 3 mod 4, right? So try it, see what happens. Let's see here. So we just got to work through the possibilities here, I suppose. 0 squared plus,
1 squared.
I mean, I guess we could do 0 squared plus 0 squared. We could do 0 squared plus 1 squared. We could do 0 squared plus 2 squared.
1, 2.
We get, yeah, 1 squared plus 2 squared.
1 minus 1. Or that's the same.
That's the same, right?
Yeah, I think that's the same. 0, 1, 1, 0, 2. 1, 2. Yeah.
I guess we could have 2 and 2, right?
Oh, yeah.
All right, so this calculations can be done mod 4. What do we got?
0, 1, 4, 5, 8.
So you got 0, 1, 4, you say 5, 8. Now that's congruent. 0, congruent to 1. This is stupid. Congruent to 0, congruent to 1, congruent to 0. There is no 3 there. Hey. 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 Jerk. Come on, man. It looked like it looked legit, but it's sad. So no 3. Therefore, x squared plus y squared is not congruent to 3 mod 4. Which again implies that there does not exist a p of the form 4z plus 3 such that x squared plus y squared equal to p. So this is like a pretty easy argument to prove the impossibility of certain forms of numbers coming out of this quadratic form. So this is one of those results which was discovered by Fermat. But this is not how Fermat did it. Fermat used this technique called descent, which is a much more technical, involved thing, which I certainly couldn't explain to you today. So I think that's just like a really neat example. And there are others of these that you can check. Like here's another one. Example 2. You can show that x squared plus 3y squared equals to p has no solution for p in 3z plus 2. So it does not, this will not output a number of the form 3, a multiple of 3 plus 2. And so to do this, you can just check, you can calculate mod 3, and we need to check, so mod 3, there's just x equals to, let's say 0, 1, and 2, x and y equal to that. So you can look at it, 0 squared plus 3 times 0 squared, right? 0 squared plus 3 times 1 squared, 0 squared plus 3 times 2 squared. What are those, And what else are the possibilities? 1 plus 3 times 1. Well, I guess 1 plus 3 times 0. 1 plus 3 times 1 squared. 1 plus 3 times 2 squared. What are the other possibilities? 2 squared plus 3 times 0 squared. 2 squared plus 3 times 1 squared. 2 squared plus 3 times 2 squared. Right? You have two inputs. You have 2 inputs. There are 3 possibilities. That means there are 9 cases to check. There were actually less cases in the previous one because of the symmetry of the problem. You know what I mean? Like the fact that x and y are both squared, there's no weights. X and y appeared symmetrically in the previous problem. There were less cases in the previous problem. In this problem, there are 9 cases because of the 3 in the quadratic form. But you work it out, what do you get? Yeah, work it out. We got. So you said you got 0. You got 3, which is 0, by the way. Yeah. You got 3. So that's 0. That's 1. That's 1. That's 1. 4. 1. That's 1. 1. Right. So as you can see, you get zeros. You either get 0 or 1. You never get 2. So there's no p of the form 3z plus 2. You can feed numbers all day long into x squared plus 3y squared. You're never going to get back something of the form multiple of 3 plus 2. So this is yet another application of modular arithmetic as it applies to solving what's called the Diophantine equation.
Did they not try this for the...
This is also a result of Fermat.
Yeah. But this is what we were talking about in the video, right? The x squared plus ny squared equals to 1. Is that just the Diophantine equation?
X squared plus...
Pell's equation.
Pell's equation. I'm glad you brought it up. That's our next topic.